This is the optical waveguide testing setup, where we have a waveguide here to show you, and the point of this is to have a way to direct light around the chip, basically the same way fiber optics do, but at a chip scale. So we can, it's basically like a wire for light. So instead of using copper to transmit your information, we use light, because it offers like 100 times more bandwidth than copper can do. So we have a bunch of devices that are going to need this. We have modulators for converting electrical signals to optical, and we have detectors to go back from optical to electrical. We have resonance structures that provide filtering, wave-type multiplexing, all done in these waveguide devices. And the main application is optical interconnection between computers. Basically, people have high-performance computing clusters where you need to transmit incredible amounts of information at high speed between the computing cores. So people are moving away from copper to optical connections. So we can make a chip that provides the interface between the electrical domain to the optical. So you can picture a ton of computers with a mess of fiber connecting them instead of copper cables. With advantages on the optical signal that you can't do on the electrical signal. And you can do it at super high speed because the bandwidth of optics is like almost unlimited. You want to see just how important this is? If I just turn this positioner a little bit, you can see the power on this meter here. It's going to just disappear when I move the fiber like 1 micron away. Sure. Yeah, that's here you go.
That's 1 micron.
Comes back.
That's actually less than 1 micron.
Oh, I see.
When it turns a little, it's like more than 20 to 50 nanometer, which is 1/20th of a micron.
Enough to listen.
Yeah.
You just move it a little bit, and it's kind of amazing. So this thing lets you get a lot more tolerance. So if you were packaging devices, the difficulty of doing that is like drastically reduced. You could do it much faster, with better efficiency, because you can have some errors and still get good coupling. It's got simulations for various geometries. If you want to make light do a right angle turn, you can do that with a wire. You can't do that with a waveguide without special consideration. So yeah, it's simulating these. This one is making a closed loop. Right. Yeah, this is a special structure for modulating light. This thing.
When you say modulating, what do you mean?
Basically, you put in a constant stream of light, and you want to put data on it.
Oh, so you're on and off.
Basically blinking it on and off. You put ones and zeros on there. And this thing's got a footprint of like 10 by 10 micron.
Right now, this one is this one we can make it 13 by 3 or 27 by 4. Micron, yeah, 4 micron.
So you can put a ton of these structures in a complicated network on the chip. Or you can think of a switching fabric, a cluster of computers all communicating with light. You need to switch the signals between different paths, different computers. That would do it. And another benefit of this thing is it's super low power. It's got a resonance enhanced feature. So compared to normal modulators for telecommunications, this is incredibly